So there's this popular explanation out there for how magnetism is just the electric force but with special relativity. It's meant to be a nice intuitive explanation, but honestly, for me, the first time I heard it, I was left more confused than anything. They all tell a similar story, but there's a subtle issue that you may have spotted if you've got a good eye for detail. So typically the explanation will go something like this. The laws of magnetism tell us that there's a static magnetic field around any current-carrying wire. A charge that's stationary with respect to this field feels no force. But if the charge starts to move perpendicular to the field lines, we expect it to experience a magnetic force, the direction of which can be determined using Fleming's left-hand rule, which tells us that this positive charge should feel a repulsive magnetic force away from the wire. This magnetic phenomenon is then re-explained from a purely electrostatic point of view, using special relativity. In this way of looking at things, a stationary charge here will feel no electric force because from its point of view, the wire is electrically neutral. But if we consider a charge moving, say, to the right at the same speed as the electrons, then it's going to see those positive ions moving to the left and the electrons as stationary. Now, special relativity tells us that moving objects should appear length contracted. So from its point of view, this moving charge should see these positive ions as being closer together and the electrons as being further apart. This means that the whole wire looks positively charged, so we get a repulsive electric force. So the magnetic force that we see here can just be explained in terms of the electric force and length contraction if we choose the right reference frame. At first glance, this looks like a really neat explanation, but if you look closely, you might notice a problem. Wouldn't the moving electrons also appear length contracted in the lab's frame of reference? After all, a wire without a current is neutral, but as soon as the electrons start moving, shouldn't they get closer together, making the wire appear negatively charged in the lab frame? But this is not what we observe. The wire stays neutral. So we've got a kind of paradox. It seems like this explanation is only applying special relativity when it's convenient. Like most paradoxes in physics, we can resolve this by taking a deeper look at some of the details that may have been glossed over. Okay, so let's start with what we know to be true. First of all, we know that the wire appears neutral in the lab's frame of reference, regardless of the current. So regardless of the speed of the electrons, the wire looks neutral. But secondly, length contraction definitely occurs. So the moving electrons do appear closer together in the lab frame of reference compared to their own rest frame. These two facts can seem like they're contradictory, but to really understand how both of them can be true, we need to look at the wire as a whole system, rather than just looking at one linear section. Okay, so we have a super simplified diagram here. We're imagining some kind of crazy circuit with only 12 electrons and an invisible battery. And much like the original examples, we're pretending that there's just one layer of ions and one layer of electrons and that they're sort of neatly separated like this. So if we imagine we have a current going through here, so the electrons are moving around here at some kind of speed v, we know from experiment that the wire stays neutral. And this makes sense because there's an equal amount of positive and negative charge. So if we think about the symmetry here, all of the electrons are seen to be going at a speed v in the lab's frame of reference. So if the electrons were to appear closer somewhere, they should also appear closer everywhere else. But of course the size of the wire is still the same, so it wouldn't be possible for all the electrons to appear closer to one another, but also still fit inside the loop. So essentially what's happening is, no matter how fast the electrons go, they space themselves out so that their charge density remains uniform in the lab's frame. Okay, so if we switch to the rest frame of some of the electrons, and we can just kind of arbitrarily choose the electrons at the top here, in this frame of reference, those electrons at the top are going to look further apart from each other. So essentially, as these electrons accelerate from rest to this constant speed, their separation remains fixed in the lab frame, but in their own frame, in the electron's frame, this separation increases during the acceleration. Okay, so let's take a look at everything else going on in this frame of reference. And we're going to ignore the perpendicular wires for a second. We're going to ignore all the effects going on here, because essentially they don't actually matter, but also adding them in just makes the diagram look super messy. So just removing all of that and focusing on the things that are moving parallel to the electrons, we see that the ions and also the whole wire itself are going to be moving to the left at a speed v in this frame of reference. This means that they're going to appear length contracted. The electrons on the opposite side of the loop are moving at a speed 2v, so they appear even more length contracted. So this is how we're able to keep the total number of electrons constant, even though their distribution looks different. So in this frame, because not all of the electrons are going at the same speed, they're allowed to have different densities. Of course, this exact argument will be true in any frame of reference, for the electrons on any of the four sides of the wire. I also want to note that if it feels weird to you that there's a different number of electrons on the top row in different reference frames, you're not alone there, that feels really weird to me as well. But ultimately this is allowed under special relativity because events don't necessarily happen at the same time in different reference frames. So, for example, if we look at one electron that might be here in the lab's reference frame, that same electron at the same time in the other frame maybe hasn't yet made it around the corner. But the more depth in which we try and think about this, the more it becomes clear that this whole explanation is just an example of a very specific case. The fact is that all magnetic phenomena can be explained in terms of the electric force and special relativity, but the specifics usually require a deep understanding of the nuances of relativity. Length contraction is just one piece of the puzzle. Reference frames affect everything: time, force, mass, acceleration, pretty much every physical quantity you could think of. These complexities become clear when we try and apply this logic to basically any other situation where magnetic fields arise. For example, take something as simple as the interaction between two positive charges. If we actually look at it, it's quite complicated. In the charge's own frame of reference, there's just the electric force between the charges. But if we observe them from a frame moving perpendicular to that interaction, we suddenly get a magnetic force too, because now each charge is moving through the other one's magnetic field. And notice, in this case, length contraction doesn't affect the amount of charge seen, so the electric force stays the same in this reference frame, but we get an added magnetic force as well, so the total force changes from frame to frame. This is one of the many not so neat consequences of fully applying the messy theory of special relativity. So going back to the wire example for a moment, there we tried to explain everything in terms of just length contraction, which is only part of the puzzle, but it actually works out surprisingly well, because the electrons in the wire move so slowly that gamma is basically 1, which means that the change in force due to relativity is pretty negligible, so the magnetic force in the rest frame ends up being pretty much equal to the electric force in the moving frame. Usually though, it's not that simple. Changing reference frames doesn't just change your perspective on a force, but also the force itself. So ultimately, magnetism really is just a relativistic effect of the electric force. But to understand it more deeply, you have to go beyond the surface, because it's delving into the subtleties and the messy details where the true interesting insights tend to hide.